Well, hey, stats class. Thanks for being here today. We've got module 11 that we're working through today. I'm feeling, by the way, I'm feeling quite pumped because Linnea and I did some Just Dance 4. We did, let's see, What Makes You Beautiful, Istanbul is Constantinople, and there's another one. And that really gets you moving. So thanks to Linnea for getting me all pumped up today. Module 11, and specifically Chapter 9, is all about estimating population parameters. And it's a pretty interesting thing if you consider last chapter's perhaps impracticability. You know, it had its own practicability, but it was dealing with weights of pennies, Star Trek versus Star Wars. But did you notice how the population parameters, the average weight of a penny and the true proportion, were both known? And if you think back to Chapter 1, isn't the process of statistics saying, I want to know how a population thinks or is, so I sample it, perform statistics on that sample, and infer back to the population? Well, that doesn't make sense to do that process if we already know what the population is, right? So now we're moving into perhaps a much more practical type of statistics where we're actually saying, I don't know what the population parameter is. Why don't I do some statistics and infer something about the population? And that becomes a little bit more exciting as we go through. So we're going to start by working through the point estimate of a population proportion. Now, I think last chapter, I think we already worked through the point estimate, right? For example, I think the example I'm going to use is the Quinnipiac University poll, which we did the 1783 registered voters, whether they favor or oppose the death penalty. I think we did that last chapter, but you recall that the point estimate is going to be how many people think a certain way, how many people did you ask? That is the point estimate for the population. Okay, it's just an estimate because we didn't sample everyone. So let's say we've got this Quinnipiac University poll. 1,783 people were asked if they favor or oppose the death penalty for persons convicted of murder, and 1123 said they were in favor. So if we did a point estimate, that would just be 1123 divided by 1783. I think it's 0.6398 or something. 0.630 is what we get. 63% of the population thinks that way. Or does it? 63% of that sample did. But can we then infer that 63% of the population thinks that way? So what we're going to do is create this thing called a confidence interval. And yeah, we are estimating values of population parameters. We didn't find the actual value. The real value is out there somewhere. We just can't obtain it very easily. So we're going to create this confidence interval, and things get a little potentially confusing as we go through here, especially when you get into some alpha stuff and some z-scores. But hang with me; it seems pretty easy once you have worked through it all, especially when we've got the availability of StatCrunch. A confidence interval for an unknown parameter is an interval of numbers created using the point estimate. So if 0.630 is what the sample said, maybe it's not 63 exactly. Maybe it's between 61 and 65, right? That becomes our confidence interval. Or maybe it's between 60 and 66, or maybe between 62 and 64. And right now we're going to work on how do we even determine that? Are we just making these things up as we go, or is there a mathematical science involved in determining just how wide that interval is? But it is a range of values we expect the true population parameter to be within. And that's kind of a key thing. If 63% say this, whatever the real parameter is, can I create a window wide enough that I guarantee the real thing is in there? That's what I want to find out. And interestingly, the larger the interval, the more unsure we are. Okay? And imagine this. Let's say that, can we guarantee that an interval will contain? Can I guarantee that the interval is going to contain the real thing? Well, actually, I can. The poll says 63% of my survey. I'm going to make an interval that says, well, somewhere between 0 and 100% is the real thing. Well, that's silly, right? Can I narrow it down from 1 to 100? How about 0 to 100? How about 1 to 99? How about 2 to 98? How narrow can I make this while still being relatively sure that I've got the real interval, the real proportion in there? But again, the larger the interval, the more unsure we are about the true parameter. Okay, so remember, the actual population parameter exists, but it's unknown. So now, here's the idea. Let's say that I take a survey, Quinnipiac took a survey of 1783. Let's say they took another survey of 1,500. They took another survey of 1,600 people. They took another survey of 1,800 people. And they took a whole bunch of surveys. And they found a whole bunch of point estimates, and they created a whole bunch of confidence intervals. There was this one from this survey, this one from this survey, this one from this survey. The level of confidence represents the expected proportion of those intervals they created to actually contain the real deal. That is what we have. So the level of confidence is denoted in this very strange way: 1 minus alpha times 100%. Don't let that notation confuse you, because so many of things, remember how we talked about what is unusual? Isn't a 5% value in the tail going to be something unusual? And that 5% in the tail could be down to 1% or 10% or 2.5%. Different things like that. So we use the alpha to represent that tail size. Well, let's say we've got 2.5% of unusual on this side and 2.5% in the tail on this side. 2.5 plus 2.5 is 5%. That leaves 95% in the middle of what I would consider usual. So that's why we have this idea. If I've got a 5% alpha, the level of confidence is going to be 95%. This is where I use the math. This is what I communicate. And what this is saying then is, I think I've got it on the next slide, a 95% level of confidence implies that if Quinnipiac took 100 different surveys, found 100 different point estimates, created 100 different confidence intervals, 95 of those intervals would contain the real population parameter. We don't know which 95, but we know that probably we would expect that 95 of them contain the real thing. Now, if we remember, every time, if we were pinned to the wall and said, you need to give me the population parameter, the best thing you've got is to give the sample proportion. But having that extended out gives you a little bit more confidence. And that takes us then to margin of error. Because if this is what the sample says, and we create this interval based on our margin of error, then, based on our confidence level, then the margin of error is going to be how far away is our point estimate from the low and high endpoints of our confidence interval. So it's like you've seen those surveys with a margin of error plus or minus 3%, right? Well, that means the point estimate is here, add 3%, subtract 3%, and that gives you that confidence interval. And it might be a very narrow thing, it might be a very large thing, and it probably depends on all kinds of different factors. In fact, there are three main factors that affect the margin of error. We've got level of confidence. How confident do you want to be? If you want to be extremely confident that your interval is almost guaranteed to hold the real thing, you better make it wide, right? If you make it narrow, you're more likely to miss it, which means you're going to be less confident. The more confident you need to be, the more, the wider your interval needs to be. So that's the first thing that affects your margin of error. Second one is the sample size. Well, it probably makes sense that if you just sample a few people, you're going to have a bigger error. If you sample 50% of the population, well, you're going to have a very small margin of error. And lastly, the standard deviation. The more dispersed the population is going to be, the wider the interval is going to be. And that, again, just makes sense as well. Okay? So, conceptual versus computational. We're gonna show you how to do StatCrunch with this pretty straightforwardly. So don't worry about the using the equations and formulas on the slide to do your actual computation. But it does really help, especially as we move into chapters 10, 11, and 12, as we see some of this language worked out. Okay, so this is review. I put it in green, so as you're sliding through these slides, you'll recognize that this is all review. But perhaps you remember that a simple random sample of size n, if this thing is true, that means it's big enough. If this is true, that means it's small enough, it's normal. The mean and standard deviation are given. Why do we need the mean and standard? We always need the mean and standard deviation to do statistics. So we can find the mean as the 1123 divided by 1783, and we can find our standard deviation as this right here. So knowing that, we can construct a confidence interval by taking our standard deviation. Okay. Z-scores. Remember, what does a z-score of 1 mean? That means that you are 1 standard deviation above the mean. Remember, if within plus or minus 1 standard deviations is 68% of the data, within plus or minus 2 standard deviations is 95% of the data, 99.7. Remember those empirical rule ideas? Well, plus or minus 1, plus or minus 2, about 68, about 95, about 99.7. Those are all about. The math becomes much more precise. And there are specific z-scores down to whatever decimal value you want. There are very specific z-scores that apply to different sized tails. And you could even look up in your chart in the back, table 5, I think, in your textbook. I don't know if you still have the textbook. Never thought about that. But if you have a textbook at home, you fold out those folders. There's a little box there that has z-scores depending on different confidence intervals. And the z-score of a particular alpha is going to be maybe 2.08, maybe 1.92, depending on how far away you want. And if it's a 95% confidence level, that means you've got 5% split in 2 for a lower tail and a higher tail. That's why we have this thing right here. So we take our alpha, which maybe is 5% because we want a 95% confidence interval. We take that alpha divided by 2 and look up in a chart to find what z-score. Maybe it's 2. Okay, well then I take the standard deviation and I multiply 2 times the standard deviation and subtract that from my point estimate, and that takes me how far down below do I want to go. Again, just think about this for the sake of the normal curve. You've got your mean, you've got 1 or 2 standard deviations away. What is the boundary? Remember Kevin Garnett my wife, myself, and Candace Parker, is that the four? Who's the tallest? Kevin Garnett, I'm the shortest, because we set up our boundaries for what we, where we are in the Z-score, and it turns out that I am further below normal than any of the other three. That's all we're doing here. We're finding the middle of this, which is our point estimate, and we're subtracting away a certain number of z-scores of standard deviations, and then we're adding the certain number of standard deviations above to come up with our boundaries of what we consider normal. And the only difference is, instead of just saying, abnormal is 5%. Well, now let's be more precise. Maybe we want the abnormal to be 1%. Maybe we want to make a 99% confidence interval. Maybe we want to make a 90% confidence interval. We can make it whatever we want to know just where we are on that curve. Okay, so that's why these upper and lower bounds work. Again, we're not constructing this. We're going to have the computer do this for us, the StatCrunch. But this is really what the computer is doing. And it's not all that tough. It's just painstaking with all these different variables and constants and things. So now, how do you compute the margin of error? Well, the margin of error is just whatever you're adding or subtracting, right? You've got this. If we add this amount to get the upper bound, subtract this amount to get the lower bound, the margin of error is simply this value right here, the z-score times the number of standard deviations. That is the margin of error. Sweet. The calculator or StatCrunch, I don't believe gives you the margin of error, but please recognize how easy it is to find. All you do to find the margin of error is, if the StatCrunch gives you these two things, subtract them to give you the full range, divide by 2, and that will give you that amount. And I'll show you in an example here in just a moment. So that is pretty much all of the conceptual ideas. Now let's get to an actual problem based on that same 1783 voters, 1123 were in favor. Use technology to obtain a 90%, a 95%, and 99% confidence interval and their margins of error for the proportion of registered voters who are in favor of the death penalty. So I think I have a StatCrunch screen, and let me show you how to get there. I don't want edit. I do want to make this go away. I find it, I better sit down. I find it by going to stat, proportion stats with one sample with summary. Okay, ready? I go to stat, proportion stats, because we're doing proportions. I only have one sample. I'm not comparing two samples together, that will be later. I'm only looking at one sample and how one sample survey, how that reflects the entire population. And I don't have data, I actually just have the summary. And within this summary, I'm going to see, oh, that's right, there were 1123 successes. There were 1783 people surveyed. I want a confidence interval of 0.9 and just the standard. I don't need to store anything, and now I compute, and it will give me that. And I've computed actually all three of them. And I hope that you can see this on the screen. Let me read them to you if you need to. First of all, there are a couple things to note. This is the 90%, 95%, 99%. They're all three 1123 out of 768. The sample proportion is 0.62984. I remembered it well. That's the same for all of them. And what they call the standard error, we are also calling the standard deviation. That is the same for all of them. But you'll notice that the limits are a little bit different. I'm going to write these down so we can kind of summarize them. A 90% confidence interval is going to be between 611 and 649. The 95% confidence interval is from 607 to 652, and the 99% confidence interval is 0.600 to 0.659. Okay, so that's how I can see all those. Let me go back to my screen. Okay, so we did that. So we computed them all. And I think that I have it written down between 0.611 and 649. The margin of error is going to be this minus this divided by 2. And that's going to be a 0.019. I did not do that for these. It doesn't really, I don't have to, I suppose. Now, again, to emphasize, do these intervals make sense? This is the smallest of the intervals. This is 611 down to 607, down to 600. And it's almost like your management is coming to you saying, I need you to be accurate as possible. Give me a range where the real thing is, and your job is on the line. Well, if your job is on the line, that means he wants a really precise kind of thing. You're going to give him the widest margin possible. If he comes back and says, that's too wide of a margin, you didn't narrow it down, and you say to management and say, well, I can't narrow it down if your desire for accuracy is that important. If your desire for accuracy is that important, I'm going to give you a big range so you know that this is the range of accuracy. Now, if you don't care as much about the accuracy, if you're willing to be wrong in exchange for a narrower range, then I can give you a 90% confidence interval, which is in other words, it's the margin of error. The margin of error is plus or minus 0.019. For here, the margin of error is going to be subtract these things, divide by 2. That's going to be a plus or minus 0.03. This is a much larger margin of error. This is a 2% margin, much larger. This is a 2% margin of error. This is a 3% margin of error. If you want a lower margin of error, then you're going to have an interval, or you're going to have an accuracy perhaps that's a little bit less. And I think that is all I've got. That's a 24-minute video. I've got section 9.2 next. I hope this was enjoyable for you. See you next time.